Okay, well, thank you for your dedication to the class, and congratulations with your very successful presentations last time. I think the recordings can be used by everyone in the class as a reference for the skills, and from now on we should focus on the projects. So I will chat most of the time of the meeting about the projects, and then we'll continue our academic story about excited states. I was not sending slides because they are identical to slides for the previous lecture, number 25, before the presentation, so we'll just progress a little bit forward. And the semester will be over very quick. I'm certain that we have 2 labs available for sure, and maybe the 3 labs. So let's plan to accomplish as much of projects as possible within 2 labs, and then focus on the written reports. I'll chat something informally and then bring slides. So the major challenge is for now is to convert your democratic wishes, your interest to certain projects, into atomistic models, and since the molecular dynamics calculations always take noticeable time, I suggest that when we meet tomorrow in the lab, we will set up a plan so that by the end of the meeting, everyone does have the working atomistic model. So if you already have certain atomistic model in mind, please create a specific directory for it and try to optimize, try to build directories for characterization. If you are not yet certain, just wait. We will we will solve it one to one, and I'll prepare some models to help you if you are not sure. But the goal, the milestone that by the end of the tomorrow's lab, each of us will submit heating and molecular dynamics for the preferred project. So there are multiple steps that either need or can be done towards the projects, but since heating and molecular dynamics are most time intense, and the models that we will be using for the projects will be substantially bigger than the learning educational models that we processed in the learning labs. It is important to submit jobs on one lab so that by the time of the next lab it will be available. So I'll do a quick comment right as we go. So for the learning labs, we all were submitting to the debug queue, which is limited by less than 30 minutes. And this will not help for competitive projects. For research projects, we will be replacing this debug word by the word regular, and then the permitted length of a job is 48 hours, and the jobs may wait in the queue up to 3 days, so that if we submit everything tomorrow, then there is a very good expectations that this most complicated and time-consuming part of the project will be done. Today, in a couple of minutes, I will go over your preferences, your list, and make some comments. And with your permission, I'll chat a little bit more right now about this diagram. Everyone is welcome to depart from this diagram. It's only a starting point, but historically it was useful for many participants of the class in the previous years. So the arrangement of the projects after you select model will be to compare this sign, these blue boxes, density of states and spectra, before and after molecular dynamics. So for heating and molecular dynamics, it is important to run these long jobs. And actually there will be two, one heating and another molecular dynamics. For characterization, when one needs just a single point, the debug queue will work again very efficiently. So for single point, if there is no optimization of molecular dynamics, basically for any system, the single point calculation that generates wave car will be sufficient. Okay, so, and let me, since it is very close here on the next slide, right now this comment is a little bit too early because we didn't finalize the models, maybe except Raju, who is very certain about what he's doing. But let me suggest that for any specific job like heating, molecular dynamics, density of states, spectra, with and without heating, there will be certain separate directory, and I am not going and I will not be physically able to look into subdirectory of everyone and check how you organize your directories, but it is your interest and responsibility to make a set of directories and names them accordingly, not for me, not for each other, only for the author. Even in our very limited time and couple of weeks long projects, from my personal experience, it is so easy to get swamped and lost in the set of files and directories. So when planning project, you may just take a piece of paper and write diagram, which jobs I want to run, how I will name the subdirectories for each job, a little map. No way it is required, but it is highly recommended just to survive. Okay, so when we were chatting about projects last time, we reviewed possibilities, and some of the figures I think did attract your attention and help you to make your decisions. So let's look on what has been selected. Okay. I have a better one. So I did shorten the list, and I'm going to go one by one with my impression of what you have selected for your projects, and what can be suggested, how it can be suggested to process. Before the start of tomorrow's lab, you still can re-decide, but I hope that most of you will continue what you already made your selections. So Amir and Yang Chao selected for carbon nanotubes for emission, and if you decide to pursue this direction, first we need to find how to make a difference between Rebecca also interested in carbon nanotube. So how to make difference between those who want to focus on it. So there is a critical aspect of any nanotube is so-called chirality. So if you are starting this project, you may want to get some initial acquaintance with chirality and the indices. So carbon nanotubes are typically referred to by two numbers, and these two numbers, for example, in here we show 11,0. So the first number approximately tells about the diameter of a tube. So how many array rings are arranged on the circumferences. The second number shows whether the tube is twisted around itself, whether it is the graphene is rolled in the rectangular way or in the at some certain angle. So the second number certifies the angle, and anything with second number non-equal 0 will be very huge simulation cells. So for educational purposes, it's better to use a chiral, the tubes without chirality. So latest update, latest opportunity to make carbon nanotubes to emit is to attach real rings in a covalent way to the surface, and one can either screen over possible geometries by making them by hand, or make a molecular dynamics of chemical reaction, how the adsorbate sets on the surface. We'll continue more. I just quickly glance through the possible projects. Zhaofan told that we are interested in interface between silver and silicon. So for processing this goal, I will need to take interview from you and get an answer at least on one question: which of the following 4 options you want to pursue, because in 2 weeks we cannot do many. So their silicon and silver can be arranged in different size cluster and different dimensionality. So silver can be taken as a nanocluster and or atom, and silicon can be taken either as a quantum dot, also nanocluster finite size, 0 dimensionality, or as a nanowire, or as 2-dimensional thin film. Each of these problems does have industrial application. So thin film is more for photovoltaics, and nanowire and quantum dot and nanocluster is more for either photoluminescence or catalysis. But please ask yourself, and I can help with building models on in each direction, but it will be not possible to pursue all 4 directions. I'm not asking answer right now, but please develop it by the time of the lab. Also, I did send to everyone the written reports from the participants of this class in the previous in several previous years, and by looking through this collections of the written reports, you may get some insight about what you will be doing in the next couple of weeks. Also, I would like to make a little disclaimer. So in this year, I was not highlighting it very much, but in all previous years, it was a free will of participants of the course. So the original idea was to make a heavy exam on theoretical background in the lectures, and the projects were offered as a bypass to avoid the exam. So if someone believes that project is too hard and exam on theorems and derivation of equations is easier, let me know. We can make a votes and make sure that everyone is happy, or the majority is happy. So the projects should be confirmed by free will of the class. So why the reports from previous year are distributed? Because there are some similar projects. Nothing is identical to what you selected this year, but if you will look for Vijay Shah, I may misspell the name, from 2 years ago. There was some computations on silicon and silver quantum dots, and you may just get an idea what to expect from this system. And while keeping going through individual projects, I will give references which individual projects from each year you may want to look at. So again, for the story about Amir, Yang Chao, and Rebecca, if your interest is within emitting carbonaceous materials for photoluminescence, one of the options is to, instead of carbon nanotube, take a flake of a graphene or graphene oxide and put similar functional group and see if it will be able to emit light. This will be smaller project and smaller size of the system, and more computationally viable. Also, let me bring a comment that most of you are involved in practical research, and you are most of you are parts of the research groups with certain principal investigator and certain set of interests. So it is very much welcomed if your projects in this course will align with interests of your group rather than opposed to it. So I don't care. I'm happy with any of the projects, but if you can set up a cooperation between your primary research interest and what you do in the class on a complementary basis, it will be a good idea. Graphene flakes were not covered in any of previous years. Mahek told that you're interested in phospholipid bilayer, and in 2 years ago, Alyssa Roberts was doing a project on original plan was to look how the interface between inorganic material and phospholipid bilayer acts in a toxic way and decomposes it, but it turned out that it is too complicated project, and later on Alyssa was looking on this hydrophilic and hydrophobic part. Big part, which is like small functional group, and then this lipid layers, and then looking how the proton can pass through if one gives it big enough kinetic energy. So basically proton tunneling through phospholipid bilayer. And there are some files to continue on this project if you're interested in, and if you look on the written reports from 2 years ago, Alyssa Roberts, you may identify where to start from or which errors to avoid. Get some ideas. So from discussion with Raju, it looks like you are having quite certain plan of what to do, and you probably already have some models. We should keep talking one-to-one, and I would like to see your plan of research, whether you accept original diagram or you do have some modification to it.
No, definitely. But thank you for sharing the slides. Not slides, the project papers.
Okay.
For previous years.
Okay.
I think that's helpful. Pretty much.
Okay, my pleasure. And for project of Raju, you are looking onto ionic conductivity, but you may also assess electronic properties like
yes.
Okay, electronic conductivity as well.
Yes.
Okay, and what Sudipta missed in last year, he didn't visualize the distance from the original center of this migrating ion and its distance along the trajectory, and you may focus on it and show it because it is a critical part of this solid electrolytes through ion migration.
Yes.
Okay. So for Salim, let's check if he's here. Maybe he's not here, but maybe he will watch the recordings. I am aware that in the research group where Salim is doing his practical experiments, there is an interest to perovskite's quantum dot that is functionalized by manganese 2+ ion. And the substantial part of the optical properties is originating not from intrinsic properties of perovskites, but from the manganese ion. From this point of view, Salim may want to start with some very, very simple, simplified model where manganese 2 plus is coordinated by two chlorine counterions and then kept in the octahedral symmetry with neutral waters, and just look for optical properties of this cluster, and then using this simple and quick model as a reference point to incorporate manganese inside of the perovskite lattice, where it is surrounded by halogens in octahedral fashion, and then these halogens are connected in a network to lead ions, and the cavities in these little cubes are filled with cesium cations that are not connected to anything, but they are just used as counterions to compensate the model. So for pursuing this model, it is critically important to use a spin polarized approach, and later on spin orbit coupling, which we didn't cover it in class, but if one wants to make it competitive, spin orbit coupling, which is an upgrade to spin polarized, is needed. So for manganese 2 plus, the number of electrons is not compensated, is not even, it is odd, and spin polarized GFT is a must, is mandated for this project. So Rebecca wanted to do catalyst and carbon nanotubes, but please think once again if you may want to make connection to your research project, so which is highly competitive, and I think you have some models already where the cavity in graphene is filled with gold. But maybe we should exchange a couple of emails discussing options. And Steven told that you're interested in metal organic catalyst. So in the 2 years ago, there was work of Christian Niles, and also I want to bring to your attention the so it was in 2018. In the same year, there was a work of Braden Wade. And in 2016, there was very, very interesting work of I have forgotten his full first name and last name, but short name is Zach. So last two works were really inspiring things, where one sets up a planar porphyrin molecule. I'm not drawing it chemically. There is a iron catalytic ion in the center, and then a small molecule like here's maybe hydroxyl attached. Small molecule attacks the ion with non-zero momentum bounces off the catalytic center, and then due to this bouncing off, it merges together with whatever was attached to a catalytic center before. So it is like reactant. It starts with reactant bumping into catalyst, and then the product departs from it. So this project by Braden and Zach were successful. The project by Christian was like halfway successful, and by looking at them you may decide if you want to do something similar what they did. Also, Rebecca, if you want to, if you do not want to pursue your gold in graphene, you may look on this options as well. Okay, so where did we stop last time, and what is the goal? So we are on the before I go to academic part, please let me know if there are some urgent questions about the research projects, something that needs immediate answer.
So we need to finalize the projects within tomorrow?
Yes. Yes.
And is there any reason that there is just certain type of material here suggested for the project, or any kind of material or polymers could be?
Oh, absolutely, absolutely. If you have your own idea about the project, go ahead. I was bringing this ballot for votes, assuming that one is selecting one of the options in this ballot. If you do not have your own certain passion to pursue certain research direction, if you already know what you want to do and it is not one of these options that I was suggesting, I am more than welcome. Just let me know so that we are working cooperatively in setting up model and making plans.
Okay.
So if you have some comments, corrections, change of plans, let's exchange emails so that I adjust to your wishes. But the quality of research is important, but the direction of research is completely your free will. So these little suggestions are only backup help.
Okay, sure.
So can I go forward with academic part? Anyone objects?
Yes.
Yes, meaning you let me go forward.
Yes.
Okay. Yeah. Okay. So we are in transit from ground state DFT to theories for excited state, and right now I'm going through review. So feel free to lean back and relax. I will give you a warning when there will be new material. So ground state DFT operates with self-consistent cycle, and it is important that density is fabricated out of orbitals, and these orbitals self-consistently updated in the cycle. When technical details about functionals, if we generalize the procedure of constructing density out of orbitals, we may accept two advanced improvements. First, that instead of summation of absolute value square from first to highest occupied orbitals, we can go over any orbitals above HOMO. And this is what was covered by Mafek in last lecture in presentations. And second update, that the indices of the orbitals do not need to coincide. We can make them random, and then we just need to put weighting factor in front of them. And this weighting factor is traditionally called density matrix because it has two indices, it is a matrix, and it helps to find total density. If it is a ground state, then this density matrix has non-zero elements only on a diagonal from first to the HOMO. And if it is excited state, it is something different. This general way for constructing density out of orbitals can be chopped onto 4 segments: ground segment, excited segment, and transition segments. And the relative value, relative intensity of elements in each of these segments depends perturbatively on the strength of electric field. So if there is no electric field, if system is in ground, there is only this ground when summation goes up to HOMO. And if there is a weak, small intensity electric field, there will be some non-zero elements in ground excited, so up to HOMO and from LUMA to infinity, or from LUMA to infinity, and then from 1 to HOMO. So this cross terms first order. And if the field is really intense, or if we assume that excitation did happen, then we do have some non-zero values in this excited segment. So it comes from perturbation theory, where interaction between electric field and the dipole is perturbation. So here the next step is that we consider a very small system, or we consider a very small segment of this density matrix, HOMO segment near HOMO LUMA, and few elements below and above. Then these 4 segments are highlighted by colors. So white is ground, green is excited, and this blue and yellow are ground excited, excited ground. Since at low intensity field the excited ground and ground excited are getting perturbed first, we are focusing and formulating the goal as to find dependence of this ground excited ground elements of density matrix as function of the frequency of the incident light. So we are looking for response of the density matrix and consequently the density onto external oscillating electric field. Intuitively, we know that if depending on the frequency of this electric field, molecule may or may not be excited, because one needs to match resonance conditions. One technical thing that the matrix, the block of this ground to excited density matrix can be converted from matrix form into the vector form. And historically in the community of people who deal with these excitations, it is often one uses the notification or the nomenclature of the vectors x and y for these objects that we need to find. So transition density matrix under weak external field is denoted as x and y, and the goal is to find these elements. Okay. Still, you can still lean back and relax. It is I'm continuing the review. So in ground state, we have only coinciding indices, and we make summation from 1 to HOMO, and this weight function Fermi distribution for ground state is either 1 or 0, depending on whether energy is above or below HOMO. If it is high temperature, it becomes more smeared function Fermi distribution. If we approximately describe excited states as in ground state DFT as Machek did present, we can manually modify this function f, which is called Fermi weight in the VASP. And total density matrix is composed of 4 segments. We are looking on the excited to ground to excited, which we call x and y. So right now I'm starting something new, but I'm slowing. So if please start focusing. We will go slower than possible, because on this way towards reliable theory for excited states, there are some underwater stones and complications, and we need to accept some concepts and approximations. So please give me little signs if this concept, Frank-Condon principle, and if this diagram that is shown on the slides was ever brought to your attention, if you're not surprised to see it. So please answer if you ever saw a diagram of this style. Okay, I see 0 answers. Now, please let me know if you never saw a diagram like this, and if the Frank-Condon principle is a new word that surprises you.
Me.
Okay, new for one, Mahek. Is it new for anyone else?
Yes, for me.
Okay. So then I'll go over it. Oh, let me ask Stephen how new this concept is for you.
Not particularly.
Have you ever seen this similar diagram?
Yeah, they look a bit familiar, but a bit different than before.
But you saw it in your PChem course, right?
Yes.
Can you share just very general what to think, what does it related to, very general words as a starting point? And do not worry about precision or avoiding any possible errors. Just general direction of thinking. What this diagram is about.
It relates to how atoms, the different ionization energies of different orbitals change as atoms get larger and larger, and their geometry of their bond shape changes with different ligands in a crystal structure.
Okay. Not bad. So what is x-axis? And it is not an easy question. This is quite complicated question that is being discussed in scientific community for the last 100 years.
I want to say it's related to the bond length of an atom and its ligand.
Okay. Yes. Okay. Thank you, Stephen. It gives good starting point. So remember when we started the course, we were building molecular Hamiltonian for 2 protons and 2 electrons revolving around them, right? And then we were doing Born-Oppenheimer separation and separately processing the Schrödinger equation for electronic part and for ions. And the potential energy surface is migrated from solving electronic part into Schrödinger equation for molecular part. So we were introducing the concept of potential energy surface, which is total energy, or better, potential energy as function of interatomic distance. Okay? So for the, and in the molecular hydrogen, there is, in diatomic molecules, there is only one parameter that describes the geometry of molecule. As soon as we have more than 2 atoms, it becomes multidimensional space. But one can find a path that describes most important active coordinate. So everyone should be happy and not surprised with potential energy surface for the ground electronic state, right? And if we accept that molecular Schrödinger equation for the nuclear part that nuclear part has wave function and is quantized. Then there are wave functions, nuclear wave functions. Near equilibrium, they look like harmonic oscillator if it is one-dimensional. If it is something more complicated, it becomes Morse and then multidimensional functions. But there is a very simple, trivial, but important fact that I believe we all will happily accept. So if the system experiences excitation, and I'm echoing some of the information that Stephen has contributed. So if we do excite system, shapes of orbitals are being changed because we promote electron from occupied to unoccupied orbitals. Density becomes different, energy profile becomes different, forces become different. So the interatomic forces between ions are different if the model is excited, which means that the potential energy surface for ground and potential energy surface for excited are different. So what you see here, the red and black curves, it shows how the potential energy surface differs depending on ground and excited state. In the very oversimplified way, the main characteristic is that the equilibrium geometry, if we forget about nuclear quantum effects, if you look on the geometry, then equilibrium geometry in ground state has one interatomic distance. But if the system is in the excited state, then equilibrium geometry, the minimum of the parabola, is at the different position. So basically, you excite molecule, and bonds often loosen, sometimes shrink. So interatomic distance changes. So what are consequences of this change of interatomic distance onto spectroscopy? Let me ask Stephen once again, because you already contributed some ideas, and they really helped all of us. So can you please comment what are the consequences of this change, of this effect, of the change of the interatomic distance onto spectral features of molecules?
It would shift the emission spectrum pretty dramatically, since each orbital level has a characteristic excitation energy and spectrum emission, wouldn't it?
Super. I applaud you. It's absolutely correct, and I'm happy to hear it. Rebecca?
Yes?
Can you please comment on this? Would you agree with Stephen? Would you verbalize it in a maybe different way?
Can you repeat it once, please?
Can you please interpret what are the consequences of the different potential energy surface for ground and excited state on the spectral signatures of a molecule?
What do you mean with signatures?
Transition energy for absorption and emission spectra.
So you mean that it's like peaks and not only straight lines?
Position of the main peak, like absorption and emission, typically well, there are some complicated structure, but one can identify most intense peak in absorption and most intense peak in emission.
Yes.
Are they expected to coincide or not?
Yes.
Yes mean coincide, or no, or yes meaning they are expected not to coincide?
They do coincide?
No. So please express your arguments why they should coincide.
Isn't...
So let me try to give the argument that you're probably thinking about and wanted to bring up. If we do have HOMO and LUMO orbital, if we do excitation, then electron goes from HOMO to LUMO. It is transition energy. If it makes an emission, it goes from LUMO to HOMO, same transition energy, right?
Yes.
No. Because if in this statement we assume that geometry, that bond distances, interatomic distances, stay the same during absorption and emission, right? But it is not the case. It is as soon as we promote electron from HOMO to LUMO, interatomic forces are different and molecules start changing its shape and start changing energy difference between HOMO and LUMO.
Okay.
Okay? So this effect was observed and recorded on experiment many years before any quantum theory and computational chemistry. So it is objective observation in spectroscopy, in experimental chemistry and physics. And in vast majority of the molecules, the transition energy for emission is smaller than transition energy of absorption. So if I want to oversimplify, if molecule absorbs in blue color, then it will emit red color. So red shift. The transition energy experiences red shift, or if you speak on the language of wavelengths, then wavelengths becomes bigger. So red shift. And the name of the scientist who recorded is Stokes. So it is Stokes Shift. And here in this class, in the computational chemistry, we are able to quantitatively assess this property. So let me attract your attention to the diagram. So let's start from the ground state equilibrium point. Then a photoexcitation leads promotion of electron from, let's say, HOMO to LUMO to the excited state potential energy surface. So we arrive to the same value of the coordinate, but different surface. Then, next step, since we are not at the equilibrium position anymore for excited state surface, the geometry starts to relax, to re-optimize to its new equilibrium position, right? No one objects? And then, if system does want to emit light, if there is by Einstein coefficients, there is a need, there is a favorable opportunity to recombine back to the ground state, this recombination goes from different geometry, from the equilibrium position of the excited state surface to the ground state. And you see here that what I was drawing by yellow and by black has different transition energies. The excitation energy is bigger than emission energy. Right? So in this diagram, we are calling the excited state potential surface by ES and ground state potential surface by GS. Then we do call the equilibrium position of ground state by RGS and equilibrium position of the excited state by RES. So in order to assess the amount of the Stokes shift, we need to subtract the height of the excited state potential surface at ground state geometry minus value of ground state potential surface at ground state geometry. So this will be absorption. For emission, we are subtracting excited state at excited state geometry, this point, minus ground state potential surface at excited state geometry. So this will be emission. And if we subtract absorption minus emission, we are getting the difference between transition energies of absorption and emission, which is referred as Stokes shift, and it is experimentally recorded for any molecule. So if we draw a spectrum, then for most organic molecules, UV spectrum, then it will look to hold mirror symmetry approximately. So absorption will have bigger energy, emission smaller energy. Or if we are using the units of wavelengths, the absorption will be at shorter wavelengths and emission at longer wavelengths. The difference between this tallest peak in absorption and tallest peak in emission is experimentally referred to as Stokes shift. Let me ask who was not speaking today. Mahek, may I ask you about interpretation of this effect? So let me formulate the question. Suppose we do have two molecules. One molecule has very loose, soft interatomic interactions, and another is very hard, so that interatomic distances are not changing. In which molecule Stokes shift will be bigger?
The one which has loose molecule?
Yes, perfect, absolutely correct. So for molecules that have single bonds, that there are groups, like ligand groups, that are connected by single bond to the rest of the molecule, there are a lot of modifications of geometry, and they experience larger Stokes shift. For stiff molecules or solid states, like crystals, dielectric crystals, or such for carbon nanotubes, the amount of the Stokes shift is very small. So one of the characterization of a system is to say, like looking on a spectra, one can say whether the bonds are stiff or loose. So big Stokes shift, loose bonds; small Stokes shift, very hard bonds. Okay?
Okay.
Yeah, thank you.
Hi, Dr. Kelly.
Yes.
I have a question.
Please.
So there are two potential energy surfaces on ground state and excited state. So my question is, the well depth or the width of the potential energy surface is different, or the two curves are exactly the same?
There is no theorem telling that they are exactly the same. Generally, their shape is different. But since humans are not very strong, since we need to accomplish certain results in limited time, it is very common approximation to assume that shapes of the potential energy surfaces are the same for ground and excited state. So it is not absolute truth, it is an approximation. Okay. And here I was just browsing online for some examples of Stokes shift. So this is small Stokes shift. You see it's like less than 100 nanometers in the infrared region for the lanthanide dopant in the crystal. So in crystals, the Stokes shift is small. It's like about less than 100 nanometers. For molecules, it is much bigger. And typically, the emission is red shifted comparing to absorption. So larger wavelengths means red shift. Okay. I think we are over time, and we got to a logical point that it is good for today. But as a summary, the goal is to set up a theory for transition density, to see a response of transition density to perturbing electromagnetic field of different frequency. Instead of pursuing this goal, today we deviated to response of interatomic distance onto excitation. But this is an effect that needs to be taken into account if we are dealing with small molecules. If we wish to neglect it, we need to give very strong justification, and objectively it gives a complication. So developing a theory for excited state for fixed geometry can be dangerous, because geometry is changing if one is exciting the molecule. And as you progress, as you are getting involved into electronic structure community, you frequently hear that someone is doing excited state optimization. Like Rebecca may have heard it from Levi and Janet. So here I suggest we finish. Everyone is welcome to disconnect. I'll stay here to answer questions if any.